Hello and welcome back. In this lesson we are going to learn about gravity and gravitational potential energy. So let's get started. To understand gravitational potential energy, we need to understand gravity. What is gravity? Gravity is a fundamental force that exists naturally in our universe. Its effect causes objects that have mass to attract each other. It's a relatively weak force, but it gets quite strong when the masses involved are large. So, what do we mean when we say objects that have mass attract each other? To understand that, let's look at this skydiver falling towards the ground or the Earth's surface. Both the Earth and the skydiver have a finite mass, and hence there is a force of gravity or attraction between them, but the Earth's mass is very large compared to that of the skydiver, and therefore Earth exerts a much stronger force of attraction compared to the skydiver. This attractive force pulls the skydiver down towards the Earth's center of mass. This force is what we call gravity or gravitational pull. It causes an acceleration in the skydiver's downward motion. The value of this acceleration is what we use to numerically express gravity. Therefore, gravity is expressed in units of meters per second square. It's also quite common to express gravity in newtons per kilogram, which may be a bit more intuitive in terms of gravity being a force. But both these units are equivalent, and newtons per kilogram when simplified equates to meters per second square. While gravitational pull increases with increasing mass, increasing distance has an opposite effect on gravity. As the distance between the objects increases, the gravitational attraction between them decreases. After a certain distance, gravitational pull is no longer noticeable. This applies to all objects, including Earth. The distance or the region over which the gravitational force of attraction is noticeable is called the gravitational field of the object. For Earth, gravity is typically noticeable through the Earth's atmosphere, though it decreases in strength as you reach the upper layers of Earth's atmosphere. Here you see some of the planets in our solar system, and we notice that the bigger and heavier planets like Jupiter have a much stronger gravitational pull than Earth. Similarly, objects smaller than Earth like our Moon have a lower value of gravity. For example, the gravitational pull on the Moon is roughly 1/6 of that on Earth. While gravity increases with increasing mass, it decreases even more rapidly with increasing distance between objects. It's interesting to note that this complex interaction of distance and mass and the resulting gravitational pull between the planets and Sun is what causes the movement of planets in our solar system. Now that we know about gravity, let's briefly talk about weight and what it means in physics. We have all expressed our weight in kilos at some point, but when we say that, we are actually talking about our mass. You'll find it interesting to note that weight, unlike mass, is a force, and like all forces, it is expressed in newtons. This is because whenever an object is on a surface inside a gravitational field, its mass exerts a force on the other surface. This force is expressed as the product of its mass and the gravitational field strength, and this quantity is what we refer to as weight. So when we are standing on a surface inside a gravitational field, our mass exerts a force on that surface that can be quantified using the above formula. In reality, the weighing machines actually measure the force that we exert on them. However, they calibrate their scales to tell our mass. So it's very important to understand this distinction between weight and mass, and to realize that weight is actually a force. Now, here's a question for us to solve to test our understanding. An astronaut on the Apollo mission weighed 882 N on Earth. Calculate the weight of the astronaut on the Moon's surface. The values of G on Moon and Earth are given. Let's solve this. So we know W is m times G. So let's calculate the value of m. Now that we know the astronaut's mass to be 90 kilos, let's calculate the astronaut's weight on the Moon. W equals 90 times 1.6, which is 144. So the astronaut's weight on the Moon is 144 newtons. Now that we understand gravity, let's use it to understand what is gravitational potential energy, which is also referred to as GPE in short. We learned that gravity is a force, and on Earth it acts to pull objects towards the Earth's center of mass. Therefore, when objects gain height or altitude, they need energy to do work, to move in a direction opposite to this gravitational force. This is the energy that gets stored in objects at an altitude as gravitational potential energy. And this energy is expressed as the product of object's weight, or the force it exerts on Earth's surface, times the altitude it gains, or more commonly written as EP equals m times g times h. So, in this example, the man with mass m climbing up the stairs to a height of h will gain GPE equal m times g times h. Let's do a problem to appreciate this concept better. The man in the figure weighs 75 kilos and is climbing up the stairs towards the flag. If the flag is fixed at a height of 10 meters above the ground, calculate the gravitational potential energy of the man when he reaches the flag. Let's solve this. We know EP equals mgh, so EP equals 75 times 9.8 times 10. Which is equal to 7,350 Newton meters, or 7,350 joules. So the gravitational potential energy of the man when he reaches the flag is 7,350 joules. I hope this problem gives you a better understanding of gravitational potential energy and how to calculate it. This brings us to the end of this lesson. Please practice a lot of questions on this topic and come back to the video if you get stuck somewhere. Until then, thank you and see you in the next lesson.